Thank you everyone for tuning in today. It's really a great honor for me to be invited to speak in the annual meeting of 30 years CASPA. When I moved to the Bay Area 4 years ago, the first thing I did, I signed up as a life member of CASPA. So I'm really excited to be sharing my career experience and the area of technology I'm working on today at Intel. I know this is a semiconductor forum, and I have been working on semiconductor, but more the boutique semiconductor, compound semiconductor, for over the last 3-4 decades in academic, in the industry, and mostly serving the market for optical communications and networking. But now the optics is proliferating to the compute complex. And because the massive amount of data is generated, we need a high bandwidth, more importantly, high bandwidth density, as the shoreline density is probably more precious than the real estate in the Bay Area. We need to use every little micron of it. In the meantime, the data, high bandwidth data will burn a lot of power. The power consumption is to a point of unsustainable. So the optics come in play to interconnect between the compute complex between different XPUs and between the XPU and memory. So for example, high bandwidth memory packaging. Intel has been working on silicon photonics technology. So silicon photonics 20, 30 years ago may sound oxymoron because silicon doesn't emit light. It can do a lot of magic, but it just doesn't glow. And so Intel's technology of the silicon photonics is basically combine the compound semiconductor, the indium phosphide or indium gallium arsenide quantum well 3.5 microstructure or heterostructure on top of silicon. But silicon does really well, not only manipulating electrons in electronics, but also does well to confine photon in certain wavelength range, like 1.3 micron, 1.55 micron. So we can use silicon waveguide to combine, to split light, and we can modulate light by introducing the epitaxial technology of germanium on silicon. We can build detectors, photo detectors in there. So the only missing piece for the optical communication key component is emitting devices. The Intel's investment 20 years ago really was focusing on hybrid technology. Through wafer bonding, we can get indium phosphide, indium gallium arsenide based quantum well structure, wafer bonded onto the silicon photonic circuits, and then do subsequent processing to introduce electrodes. So this way we have the hybrid integration of laser amplifier components with the rest of the optical components. The silicon photonics as a academic topic has been extensively researched, but it's only until the recent decade that it becomes an area of the industry. For example, Intel, we first introduced our optical transceivers back in 2016. And to date, we shipped 6-7 million optical transceivers to provide data center connectivity in outer hyperscale data centers. The experience so far from our customers has been wonderful. And because we can control the wavelengths and quality, manufacturability, as well as silicon, because we use the 300 millimeter CMOS technology to build the silicon photonics circuit. So in this conference, I plan to present the design, the processes, and the applications of silicon photonics in optical transceivers, co-packaged optics, optical I/O to provide high bandwidth density and lower power, and optical sensing in a range of other possible applications. I look forward to talking to all of you and hopefully have an opportunity to collaborate with you in the future. Thank you very much.